Okay, good evening. Hello, everyone, and welcome to our CAWASA Wednesday webinars for water operators around the region. And if it's Wednesday, you know it's CAWASA webinar. And this evening, we are going to look at water disinfection for water and wastewater systems. And our presenter is Ms. Devika Rooplal. She has presented on our webinars previously. She holds a master's of engineering in process engineering and project management, and also she has she's a project management professional, PMP, Lean Six Sigma Yellow Belt, and a diploma in petroleum engineering. She has worked as a project engineer in water and wastewater treatment industry for just over 5 years, and she's now the engineer at Toshiba Water Solutions America Inc. She is well decorated with good experience in water chemistry and chemical analysis. And so I wouldn't go through her entire CV. It's going to take us, her bio is just as much. It's going to take us a better part of the session. So I wouldn't go into all of that detail, but to tell you that we have a very experienced person in Ms. Devika Rooplal to present to us this evening. So I will now invite Ms. Rooplal to make the presentation. Over to you, Devika.
Hi, good afternoon, everybody, and greetings from Trinidad and Tobago. Thanks, Mr. Joe, for that introduction. He's just adding his 2 cents or so, but like he said, today we will talk about this disinfection in water and wastewater treatment. So I'll get straight into it. It'll be pretty short from my side. And then we'll take a couple questions, and that will close it up. Feel free to type your questions in the chat. I think I would have given my email address before, so if you have questions that you want answers outside of the presentation, or you want some additional literature, feel free to reach out to me. So we say disinfection in water and wastewater treatment. And why do we need disinfection, or why do we disinfect our potable or wastewater? And this is mainly because, we need to eliminate some of the pathogenic microorganisms, which are usually harmful to human health if present in the water or wastewater. And at the same time, we are also reducing that hazardous risk to some sort of acceptable level where, these waterborne diseases can be avoided. So the disinfection of our potable water and wastewater provides some degree of protection from contact with pathogenic organisms. And these organisms, can cause things like cholera, polio, typhoid, hepatitis, and a number of other bacterial, viral, or parasitic diseases. So my little picture there below, minus the Japanese that we may not be able to translate, basically shows some of the pathogenic microorganisms that are in water. There are bacteria strains, the 0157, E. coli strain, Salmonella, which we are very familiar with, the poliovirus, Cryptosporidium, Giardia, there's other parasites. So that is really why we disinfect. So now that we know why we do disinfection, what exactly is disinfection? And is disinfection sterilization? What is the difference between disinfection and sterilization? So first I will go through disinfection. So disinfection is that process whereby a significant percentage of your pathogenic organisms are killed and controlled, whereas your sterilization aims at killing all living organisms. So disinfection will reduce to some sort of safety level, but if you're sterilizing, then you're gonna kill all of them. So individual pathogenic organisms tend to be difficult to detect in large volumes of water or wastewater. So their disinfection efficacy is most often measured using indicator organisms. And your indicator organisms, they tend to coexist in high quantities when and where pathogens are present. So for drinking water, potable water, the most common indicator would be total coliforms. In wastewater, your most common indicator will be fecal coliforms. So now that we know why we disinfect, or what exactly is disinfection, so when exactly does disinfection take place? When is the best time to disinfect? So typically for both water treatment and wastewater treatment, disinfection is the final step in the treatment process. For wastewater, it is usually after your primary and secondary treatment. If your system does have tertiary treatment, then it will be after your tertiary treatment. And like I said, it's the final step in your treatment process. So that is just before that treated water becomes that effluent that is released back into the environment or enters into your water system. So essentially, when you disinfect just before discharging that water, you're disinfecting to remove any organisms before discharge. So that's why the disinfection is typically just before discharge. In terms of water treatment, again, it's the final stage. It's just a slight bit different here in that you disinfect before the water goes into your distribution system or your storage system. And this is because you need to limit the effects of any residual organic matter, suspended solids, or other contaminants remaining in your water after your treatment process. So your disinfection essentially prevents the spread of any waterborne diseases by reducing your microbes and bacterial numbers down to some regulated level. And when we say a regulated level, that is dependent on country, state. So in the case of Trinidad, we have water pollution rules, and the typical level or limit would be less than 400 mpns per 100 mils. That is for your fecal coliform, which is measured in both water and wastewater. So now we know what is, why, what, and when. So there are several methods of disinfection. So you can either have physical disinfection or chemical disinfection. So when we talk about physical disinfection, we talk about things like disinfection using chlorine dioxide, the various forms of hypochlorite, sodium hypochlorite, calcium hypochlorite, ozone, you have halogens, namely your bromine, your iodine, you have bromine chloride, you have some metals like copper and silver that can act as disinfectants, potassium permanganate, phenols, alcohols, soaps and detergents, some ammonia salts, hydrogen peroxide. You have several acids and bases that can also act as disinfectants. The most common physical means of disinfection is chlorine, which we are all familiar with. Most of our plants would utilize chlorine disinfection. So as we go on in the presentation, I will talk more about chlorine disinfection. On the chemical disinfection side, there's that disinfection by ultraviolet light or electronic radiation, gamma rays, sound, or heat. And again, the most popular on the chemical disinfection side is that use of ultraviolet light, which I will go through in a little bit more detail. So I'm only picking two out, one from physical, one from chemical, and that is what we'll explain further for the purposes of this presentation. So what are the mechanisms of disinfection? How exactly does this take place? So whatever disinfection, after, break the cell wall, damage that biochemical activity of your cell membrane, it inhibits the essential metabolic functions and enzyme activities, and it alters that RNA or DNA. The factors that affect your disinfection will be things like your contact time, concentration of disinfectant, temperature, pH, the presence of interfering substances. We will talk a little bit about interfering substances, but things like contact time, concentration, pH, temperature, I think we are all very familiar with those. So I'm not going to go into any elaborate details on those. So like I said, we will talk a little bit more about this means of physical disinfection, which is namely disinfection by chlorine, which we also call chlorination. And chlorine and its various forms are powerful oxidants, and it will kill or inactivate most pathogenic organisms, and that is why it's the most common form of disinfection. It is also very easy to obtain chlorination chemicals. That is, it's economical, it's effective, and it's easy to apply. So that also adds into, why the use of chlorine and chlorination is the most popular. And the forms of chlorine that are used in disinfection are the elemental chlorine, hypochlorite, namely sodium hypochlorite and calcium hypochlorite, and you have chlorine dioxide. So disinfection with chlorine, the reaction itself, or the chemistry that takes place, it takes place by a process of oxidation. So your chlorine is soluble in water. And if we were to just look at some basic chemical reactions, so you have your chlorine plus your water, and you have that chlorine, it splits in two, and it combines with one of the hydrogen from your water and that oxygen to form hypochlorous acid. And then you have hydrogen and you have chlorine. Now, this hypochlorous acid will further dissociate. So that is a sort of a reversible reaction where that can dissociate again into hydrogen and hypochlorite. So the fractions of the hypochlorite and hypochlorous acid is related to your temperature and your pH. And if we were to just look at this little chart that I have on the side here, it shows this relationship between your temperature and your pH. So if we were to look at this temperature curve here, that is 20 degrees C, and we just say look at a pH of a 9, we will see from this chart here at a pH of 9, it's mostly hypochlorite that will exist, right? There's a higher percentage of hypochlorite as opposed to the hypochlorous acid. If we look at a pH of about 6, you would see it would have a majority of the hypochlorous acid, which is the HClO, as opposed to the hypochlorite, which is the OCI minus. If you look at a pH of about 7.5, you would realize like it's 50% hypochlorous acid and 50% hypochlorite. We should note though that your hypochlorous acid has a greater disinfection potential than the hypochlorite. So just to continue with the reactions, if you have ammonia present, your chlorine will react with ammonia to produce chloramines. Chloramines are also, disinfectants. So there's that three equations there that basically describes that reaction of ammonia with your chlorine. And the proportion of your chloramine species will depend on your ratio of chlorine to ammonia. So if we have like a chlorine to ammonia ratio of less than 5:1 and your pH is between 7 and 9, you basically will have monochloroamine forming. If your chlorine to ammonia ratio is again less than a 5:1 ratio, but your pH is around 6, you will have like 80% monochloroamine. If your pH is less than 4.5, you can have trichloroamine existing. And then this balanced tree, the three equations that I have after is really those three equations that shows if you're now using sodium hypochlorite or if you're using calcium hypochlorite as your disinfectant, and then finally chlorine dioxide as your disinfectant. Right, so when we already talk about chlorine, so the important thing here, what we have to come to now is this chlorine dose. How much chlorine do we add to, have this disinfection ability that we're talking about? So when we're talking chlorine dosage, just two things to consider. There's a chlorine demand and then there's a residual chlorine. So your chlorine demand is basically that chlorine that is consumed to kill your microorganisms and oxidize that organic matter that you have existing in the water or remaining in the water, and whatever reductive substances is there. So that chlorine demand is, the amount of chlorine you need to overcome that within your designated contact time. Now your residual chlorine is the chlorine that remains after the designated contact time and after that chlorine demand is met, basically. So if we look at this chart that I have on the top right hand side of the screen here, that blue line, so it basically is a plot of your residual chlorine versus your chlorine dosage. So that blue line is in an ideal world where there's no chlorine consuming items in your water. So whatever you dose is residual because nothing is consuming that chlorine. Now we know that that situation really doesn't exist, that ideal situation. So what in reality, we're more where this red line is. So there is some point where you're dosing chlorine, but you're not seeing a residual chlorine. And that is because the water is using up that chlorine to meet the chlorine demand that it has. Once it meets that chlorine demand, then as you continue dosing, you will see that residual chlorine is starting to increase. And this is where there's no ammonia. So this is just, chlorine consuming items within your water system itself. And when we talk about chlorine consuming or reacting species in your water, there are some organic materials that is commonly found in your wastewater that takes precedence in reacting with your chlorine. And these are things like your hydrogen sulfide, your ferrous iron, manganese, nitrite. So these would react, would take precedence in reacting with chlorine. So if we were to come back now to, and I want to bring here a sort of a real situation here. So we have a chlorinator that is going to dose, or let's say 50 pounds of chlorine per day. Our wastewater flow is 0.85 million gallons per day. And we have done a residual chlorine test, and our residual chlorine is 0.5 milligrams per liter. So what we want to know is, how much chlorine are we dosing then to get this 0.5 milligram per liter residual? And what exactly is the chlorine demand of our water? So if we look at this little pie chart that I have on the left side, bottom left of the screen, it has pounds per day in the top half, and then the bottom half is divided into flow, which is in million gallons per day. So that's the MGD. Then you have the concentration, which is milligrams per liter, and then you have this 8.34, which is a constant that really is the density. So the top half, which is the pounds per day, is equal to the bottom half, which is the million gallons per day by the concentration by this 8.34. So if we need to find this dosage, we want to find this milligram per liter. So that will become the top, which is your 50 pounds per day that we are dosing, divided by our flow, which is the MGD, the 0.85, multiplied by our density, which is the 8.34. And we will get a chlorine dosage here of 7.1 milligrams per liter. So we are dosing 7.1 milligrams per liter, and we are getting a residual of 0.5 milligrams per liter. So essentially, our water, our chlorine demand is now 6.6 milligrams per liter, because that is what is being used up, because we're giving 7, or we're dosing 7.1, but after, when we're measuring, we're only getting 0.5 milligrams per liter. So if we were to move now onto this chart that I have on the bottom right side, this is where we talk about breakpoint chlorination. So breakpoint chlorination is the point where the demand for chlorine is fully satisfied in terms of your chlorine addition to water. So in your wastewater treatment, your breakpoint chlorination is a means of eliminating your ammonia, which is converted to an oxidized volatile form. The addition of chlorine to water that contains ammonia or nitrogen containing organic matter produces an increased combined chlorine residual. So your breakpoint chlorination is a point where the chlorine level exceeds the oxidant demand and the water begins to build a residual of free available chlorine. Theoretically, exceeding your breakpoint prevents increased levels of disinfectant byproducts like your chloroamines. So if we just look at section 1 of this curve here, there's no residual chlorine present. So again, it's residual chlorine with dosage. So you're dosing, but you're not seeing a residual, because again, your water is, you have to overcome that chlorine demand of your water. In section 2 now, you are dosing chlorine, but your residual starts to increase. So your chlorine plus your ammonia is becoming things like your chloroamines. When we look at section 3 though, um, you are dosing your chlorine, but your residual starts to drop. That is because now your chloroamines are dissociating and your residual chlorine is now dropping. So that drops until until what we are calling the breakpoint, where it starts back to increase, and it starts back to increase at the start of section 4, where you continue dosing, but your additional chlorine now exists as free chlorine. So as you continue dosing, your residual chlorine increases. So here really is, this just shows you the relationship between your disinfection and the factors that affect disinfection. So the first curve, which is on the top left side, shows the effectiveness of your chlorine with pH. So a lower pH will result in a more efficient use of your chlorine as a disinfectant. If we look at the next curve, which is the one at the top middle there, a higher dosage of your disinfectant will result in a more rapid disinfection. If we look at this bottom left curve, which is disinfection again with temperature, a higher temperature will result in a more efficient disinfection. And if we look at the bottom middle here, which is the disinfection with contact time, longer detention time will result in a higher degree of disinfection. If we look at the curve to this extreme right here, this is basically the disinfection equipment if you're using liquid chlorine. So that basically, it's a schematic of your chlorine tank, the chlorine injector, and then the associated piping. And then this bottom one here, really, it's the instrumentation associated with your chlorination system. And moving now from chlorination, which was the physical means of disinfection, to now chemical disinfection. And here I'm going to discuss this ultraviolet light. UV a UV disinfection, which is your ultraviolet light disinfection system, transfers electromagnetic energy from a mercury arc lamp to an organism's genetic material, that is its DNA or RNA. So when your UV radiation penetrates the cell wall of an organism, it destroys the cell's ability to reproduce. So you have UV radiation being generated by an electrical discharge through mercury vapor penetrating the genetic material of microorganisms and retarding their ability to reproduce. So UV with a wavelength of between like 240 and 280 nanometers has a strong disinfection ability. UV with a wavelength of 250 to 260 nanometers can be absorbed by DNA and RNA. You have three main types of UV light: low pressure, low intensity UV lamp, a low pressure, high intensity UV lamp, and then a medium pressure, high intensity UV lamp. And if we look at this illustration that I have at the bottom here, ultraviolet light, it is invisible light with a wavelength anywhere between like 100 and 400 nanometers. But the band A, which is between like 320 to 400 nanometers, that is what produces like a tan on human skin, but it is a poor disinfectant. It doesn't have a strong disinfection ability. Similarly for band B, which is about between 275 to 320 nanometers, the band C, which is a shortwave ultraviolet light, which is between 200 and 275 nanometers, has some sort of disinfection ability. So that is, the spectrum or the wavelength of UV light that can do this disinfection. And band D, which is between like 100 to 200 nanometers, it basically generates ozone in air. Again, the effectiveness of your UV disinfection system will depend on characteristics of your wastewater, like the intensity of your radiation, the amount of time the microorganisms are exposed to the radiation, and the reactor configuration. Similar to that of chlorination, again, concentration, contact time, characteristics of the wastewater. So water or wastewater, it's the same thing. There are several, unique advantages and disadvantages of ultraviolet light. So the UV light is effective in inactivating most viruses, spores, and cysts. It is a physical process and not a chemical process. Hence, it eliminates the need to generate, handle, transport, or store any toxic chemicals. There's not that residual effect on, harmful residual effect on humans or aquatic life. Like if you have a high residual chlorine, that could be harmful to humans or aquatic life. But in the case of UV radiation, that is not the case. It has a shorter contact time as compared to other disinfectants. Typically, chlorination would be, around 30 minutes, some cases a little bit more. UV radiation is, in a matter of a couple of seconds, 30 seconds, 45 seconds. It requires less space than other methods. When we look at disadvantages, low dosages may not inactivate some of your viruses, spores, and cysts. Organisms can sometimes repair and reverse the destructive effects of UV via photoreactivation. So, you can have organisms, repairing themselves and re-existing and persisting within that environment. You will need a preventative maintenance program to control like your tube fouling. Tubes frequently have to be replaced because you have like light bulbs being blown, The dosage is reduced after a certain amount of hours usage. Turbidity and suspended solids can render UV disinfection ineffective. UV disinfection is not suitable for secondary effluents and effluents with total suspended solids greater than 30 milligrams per liter. And with that is where I will kind of end, the presentation part and sort of open the floor for any questions that you may have.
All right, colleagues, thank you, Devika, for a very comprehensive presentation. And now the floor is open, colleagues, for any questions you may wish to pose. I know some of you are doing some of the exams, and certainly the chemistry part will be on these papers. So it's a good, in addition to what you're already doing with during the tutorials, this may be very useful. So I think it's a good opportunity to pose your question. You can unmute your mics or post in the chat box. Doesn't seem we have anyone with any questions, Devika. I'm not hearing from anyone. Oh, there's a question in box. What is the impact of high turbidity on chlorination?
Can you just repeat the question?
Yeah, it's in the box.
Does high turbidity affect chlorination? Well, yes and no, because more yes, because your turbidity would be as a result of something, and if that cause or of that turbidity is consuming your chlorine, so it's whether that is affecting your chlorine demand. If it is increasing your chlorine demand, then you will end up dosing more chlorine because you have to overcome that chlorine demand.
And the other question was, what is the impact of high turbidity on?
What is the impact of, so that is what I kind of explained, that if your turbidity is high, depending on what is causing that high turbidity. If it's organic and that is going to react with your chlorine, then you will have a higher chlorine consumption. So, you'll take longer to overcome that chlorine demand. So, you'll find that you're dosing chlorine, but you're not seeing a residual. You're measuring residual chlorine, but you're still getting zero. Because whatever is in that water, because something is there that is generating this turbidity, but it's also reacting with your chlorine.
Any other questions?
Yes, hello, good day. I have a question,
Please.
I know you touched on it a bit earlier on, but I was going in and out of service. But the question would be, if you are about a new water treatment plant, you would have an idea of what your residual you would want to be in your distribution system. You might not be able to know what your demand is. So how do you go about selecting the correct dosing rate for that new system? Where do you start?
So that will basically be, it will be a sort of trial and error, or some band scale laboratory testing where, you kind of have samples of your water. You do this benchtop testing. I'm not sure if you're familiar with, this jar testing procedure where you kind of take samples of your water. So it's on a smaller scale, but you simulate basically your plant. So you have an idea of what you should be dosing to give you that residual. So let's say your distribution system, you need to maintain a residual of 0.5 milligrams per liter or 0.3 milligrams per liter in your distribution system. Now, there's no way to firmly tell you how much chlorine to dose, because it's, you know, it's a dynamic continuous process in that your wastewater or your water concentration is never going to remain constant. You have an idea, you have a range of, okay, well, you know, this is what my organic content is, this is what my pH is. So you will have an idea, but to be exact on, you will never be exact, but the approximations, or you know, working out with a general average of this is what my wastewater composition is. So this is what I'm gonna do. And basically, I think that is where we went through this chlorine dosage section here. And it's really, you know, you set your chlorinator to something, and you just have to go through the process and calculate, see what is coming out at the end.
Yes, because we don't have the equipment for the jet test, and we actually do the trial and error. That's what we do down there. So I just want to know if we are in the right direction. Thank you very much.
Yeah, that is essentially what it is.
Yes. Very good. I'm not seeing any other questions. Do you have any other questions? You feel?
I think there's one here, and the disadvantages for disinfection, where you be like, listen, that organisms can sometimes repair and reverse the effects of UV. What types of organisms would this be? So what tends to happen is your younger bacteria will tend to die quickly, right? So those don't tend to reactivate themselves. But if you have bacteria that is greater than 10 days old within your system, they start developing basically immunity or resistance to your light strain, and they themselves starts adapting somewhat, you know, to what humans do in terms of, you know, your response to viruses or disease. It's sort of similar. So they basically build some sort of resistance within themselves and are able to repair themselves. And this is maybe a common problem that you see. It's very difficult to control your fecal coliforms. So people with wastewater treatment plants may you know, regularly have this problem, in that you can get all your other parameters right within your limits, but you tend to always have a challenge with your fecal coliforms, unless you're shock dosing chlorine and you're overdosing chlorine. But if you're using a UV disinfection system, as they did disinfection for a wastewater treatment plant, you will get BOD that is pretty much zero. You will not get, you will get COD, your COD will come down to, again, pretty much zero. You'll have very little TSS, you will have no ammonia, no phosphorus. You can do your heavy metals check, you will not see anything, and then you will do a fecal coliform test, and you will get a fecal coliform value that is above your limit. Sometimes, you know, if they do this tube test, they may be like greater than 1600, and you'll be like, so how do I get this very high fecal coliforms? And this is what happens. This coliform bacteria, because it can where you have this UV disinfection, because of that photoreactivation, and then the way the bacteria multiplies. So you have the bacteria population basically grows exponentially. So it doubles every 20 minutes. So that is, after 20 minutes, 2 becomes 4. And after another 20 minutes, after 40 minutes, that becomes 8. And after 1 hour, that becomes 16. So again, it depends on the time, the holding of the sample holding time, and which your UV disinfection time, you know, as time progresses, as the system itself gets older, the intensity of the radiation that these bulbs emit will tend to reduce.
I was on mute. Any questions? Okay.
Yes, I have a question.
Go ahead, Terry.
Is chlorine used after ozonation and UV disinfection?
There's no reason why you can't. Um, like I say, people are shocked with chlorine because they sure chlorine is going to kill. So you would have people adding chlorine after to make sure that there's no bacteria remaining. So there are systems where people use more than one forms of disinfection. I know IWA was having some studies where they were looking at combining the different forms of disinfection. So there's no reason why you can't. The only thing is when you're using the chemicals, the residual in your water will remain a concern because you can't have, having a high residual in the water could be harmful to your aquatic ecosystems and also human life that will be using the water.
Okay, why I asked that question is I read that you don't get a residual after ozonation or UV disinfection.
Right, so you wouldn't have a residual after UV disinfection. There's no residual. That is what I said in my advantages. It will, so you see, with UV, there's no residual. With chlorine, you have a residual. So if you still have any little thing in your distribution system or something, remember you're maintaining a 0.3 or 0.5 milligram per liter concentration of chlorine. So you still have some chlorine in there that can continue to act as a disinfectant. But where you're using like UV light, remember there's nothing remaining in the water. So it really depends on what your sampling point is, what your distribution is, because it's easy now to be recontaminated if your distribution network is contaminated itself.
Well, this has been very comprehensive and some good interaction. And we're just about within the hour. So if you don't have any more questions, I'd like to thank immensely Devika for taking on the challenge at within short notice. And as I always have offered, that some of you who are participating in the webinars, feel free if you should have a topic, because you have your own expertise in different areas, that you can send me an email or contact me via WhatsApp, and we can always arrange for you to make a presentation on a topic that you would of your choice, so that you can share some of your knowledge with colleagues. But this is always very good. It also helps with the personal development, which we are trying to facilitate within CAWASA. So thank you again, Devika, and wishing you a very good holiday tomorrow, albeit you're going to be on the curfew. So make the best of it. And
thanks.
And those of you who have to work tomorrow, well, some of us will, well, it's a holiday in St. Lucia, but I have to be up with the colleagues at Operators Without Borders doing the tutorials with some of our operators who are pursuing the wastewater levels 1 and 2. These tutorials take place every Thursday morning at 8 a.m., which is 5 a.m. on the west coast of Canada. So we trust that those of you who are participating will be punctual, and we have another 2.5 hours. All the best. I'm Ignatius Jean, Executive Director at CAWASA, signing off this evening on our webinar number 15, 2021 series. Have a good evening all. Bye.